All right, it's 4:31 here in France, so we're gonna get things started. Hi everyone, my name is Jeffrey Van Kessel. I'm the CEO and co-founder here at LabelFlow, and I'm pretty happy to share this first webinar with our community today. So I'm gonna share a quick introduction with you, and then I will hand over to Etienne, which is our lead data scientist
Hi
here at Lab,
everyone.
to deep dive into an end-to-end machine learning model building. Yeah, so I'm gonna start sharing my screen just to give you some context. So here we go. Uh, do everyone see my presentation? So yeah, build an AI model in no time, and we've taken the electrical distribution grid case. So as I was saying, so there are two people speaking with you today, sharing with you, Etienne, our lead data scientist, and myself, CEO at LabelFlow. So LabelFlow in a nutshell, so the company, the project was publicly launched in September 2021, and we built the open platform for image labeling. As of right now, we are 8 people in the team, and the platform was used to label more than 1.5 millions images for Sterblue, the AI-powered platform for energy companies. Um, so let me share with you really a 2-minute product demo just for you to keep in mind what the product does, and then we'll extend to a larger tech ecosystem with Etienne. So I'm just gonna come here, and so I'm actually on LabelFlow.ai on the website. So we've been working a lot to make the user experience, the onboarding pretty easy. So I arrive in the dataset page here, and I'm going to upload a little data set, let's say some birds. So I've just actually, like 1 hour ago, I got a data set from COCO with different birds, and I'm just gonna upload them here. And here we go. So everything is stored locally on my computer. So there is nothing on LabelFlow servers. And I'm gonna start labeling. So let's say that I want to label this bird. So to be honest, I'm checking my notes because I don't know every type of bird. But here we have different type of labels. So here, bounding box with many different shortcuts, so you can explore them really easily. And right click, and this is actually a white-tailed tropic. Enter, and I can continue with the right arrow, etc., etc. And of course, I can select another bird. So this one would be the let's say the headed blackbird, the yellow, sorry, yellow-headed blackbird. And of course, you can use other type of label like polygons. So just gonna make something super raw just to show you, and nothing incredible here, but that's the basic. Yeah. So here we go. Right click, and it's actually wild Cherokee. So now imagine that you've performed this on hundreds of images, so you have a really good quality data set. You can have a look actually to the different classes that you've created here. And you can also export in 2 different formats for now, COCO format and YOLO format. So Etienne will talk a bit about it just after. That's pretty much it for this short product intro. And yeah, so I'm just going to introduce you the use case, today's use case, which is actually electrical grid equipment and why is it useful to detect this equipment. So there's actually 3 main reasons. The first one is actually to update the geographical information systems to better operate the grid, for the maintenance plans, for example, to prevent wildfires, to strengthen the grid for storms, etc., to limit back and forth trips, to the office, and of course to facilitate suppliers' intervention, providing better, more accurate information. Now the what. So what Etienne is going to show you after is actually how we've trained a machine learning model on 5 different components. The first one is actually insulators. So you have different type of insulators here: tension, tension with 2 plates, 3 plates, rigid, which are at the top, 2 plates and 3 plates, and the transformers. And you will see different performance of this. What are the different steps that Etienne will go through? Actually, the first step is actually collecting images using drones or helicopters in this specific electrical grid use case. The second step is to manually label a large enough image set. So here we've done like 1,000 images, and then have a pipeline in place for machine learning models training and validation, and use this one to pre-label automatically, and then iterate again to improve the model and the different performance. So yeah, I'm gonna sorry, one sec. No, it's my fault. So I'm gonna stop sharing, and Etienne, you can take over on the presentation.
Yes, all right. Let me share my screen. Okay, can you see my screen?
Yes.
Great. So yeah, now that Geoffrey introduced you our use case, I'll be trying to show you how to build a model like easily out of simple training data sets to be used as a prototype to pre-label new images. So here we're not aiming at creating a super accurate model with very good like metrics that comes out from a very robust pipeline. We're really talking about a simple prototype model that gives you the best compromise between the time you spend on building that model and the value you can get out of it. So of course, the first part to build that model is to actually have a labeled data set. So as Geoffrey mentioned, we created a training data set that has a bit less than 1,000 images, on which you have different kind of elements. So as we saw, you can have like rigid insulators, different kind of insulators, rigid insulator with 3 plates, tension insulator with 2 plates, a transformer here, and like some other kinds of insulators. But well, we just like fully labeled those 1,000 images. And right now, what we'd like to do is just to simply build a model out of that. So to do so, we of course use LabelFlow. LabelFlow is kind of the perfect tool for you to just like drop your images. It doesn't store your images anywhere, and to like start labeling to create a training data set. But we'll see that it will also help us evaluating qualitatively our model by importing the inference of the model. On the other end, we also need a framework and neural network to make that happen. So we'll be really focused on only using everything that's the most standard. So neural network-wise, we'll be using PyTorch, which is one of the most popular deep learning libraries. And in terms of what kind of object we're going to manipulate, we'll work with what we call COCO datasets, but I talk about that a bit more later on. So to support us, I created a very simple repo. So that's public. We'll share the link with you. So that repo is a thin wrapper around a tutorial that was made by PyTorch themselves about like how to adapt a model to your own data set. And I added on top really the bare requirement in terms of code to make it possible to just train your model on COCO datasets and to actually make inferences using the model that you just trained. So I encourage you to just clone that repo and try it out yourself, but we'll do that kind of together. The first step you are like use that framework is just to clone the repo. So what I did is that I cloned that repo on a remote computer, a remote instance that has a GPU. It will just make the training faster for us to just do it together. So let's switch to another window. That's an IDE that's connected to our remote instance. And we're just inside the repo that I just cloned. Okay, I also just installed the requirements for us to make it possible to use the script inside that repo. And here you can see a schema that's included in the repo as well. That just explains how the framework works. So as you can see, that's pretty straightforward. They just two scripts, train and detect. The train script takes a COCO dataset and will create a train model out of it. And the detect script takes your freshly trained model as well as a raw dataset. So that's a dataset without labels on it, and will create annotations like labels for that dataset using that model. So if you're new to deep learning, you might not know what is a COCO dataset. At first, COCO is the name of a dataset that was created by Microsoft. It was used and is still used as a benchmark for state-of-the-art models to really evaluate them. And it gave its name to the format that was used for this dataset. So I included in this repo a sample COCO dataset to just show it works. It just, so as you can see here, it's just a simple folder containing two things. On the one hand, it contains a folder with just images. So here, for instance, okay, images in whatever format you prefer. And another thing, which is an annotation file in a JSON format, which contains some information, generic information about the data set. It contains as well an images keys. So each object is an image. It has a unique identifier, and it links to the name of the file that you can find here. There's also a list of categories. Again, each category has a unique identifier and a name. And finally, the most important part of the COCO dataset are the annotations. And so each annotation has a unique identifier. So it has several other keys. The segmentation key refers to a polygon, but we are not manipulating polygon today. So we just stick to the bbox key. Bbox is for bounding box. And here, that key refers to the coordinates of a bounding box that's drawn on an image. So that's the label, the actual label. And so that bounding box is drawn over the image with this ID, and the corresponding class is the category with this ID. So everything is really self-contained in that annotation file. And I think that now you know everything you need to know to understand the concept of that framework. So now we really like to train a model. For that, we need a data set that looks like this one. And for that, it turns out that LabelFlow has the ability to export your data set in the right format, so in COCO format. So if I want to export my data set, I just click on export on my data set. So it tells me the number of images and labels. I select COCO. And here I just need to include the images. So it will create a pretty big zip file that will just be able to be used as an input for my model. So I won't click on export now because I want to skip the transfer part between my local computer and the remote instance. But let's say I clicked on export, and then I transferred my zip file to my instance. So that's exactly what I've just done before. In that data folder, you can find here a zip file named training powerline coco etc.zip. That's exactly the result of the export. Now there's just one remaining step for it to be usable. I just need to unzip it. So here it's on the bottom part, the terminal that's inside my repo. I'm just going to unzip my file. Unzip training, blah, blah. Okay. So now it's unzipped. You can see here you've got a folder that looks like that with images and annotations, exactly the same as here, but not with the same information, of course. And now what just remains to be done is to launch our training script. So as you see, it's very straightforward. There's just one argument, which is dataset path, which is supposed to be the path to the COCO dataset, so the directory. Okay, so now I hit enter and the training should start. So as you can see, there's a first line, pretty important, saying that the training is running on CUDA, and in other terms, it means that it's actually running on the GPU of my remote instance. So as you'll see, it's going pretty fast. There are a couple of metrics that are being logged every so often. On those, you find different losses. So the loss is a metric that tells you how the model fits the data set that it's being trained on. And of course, you expect that loss to be decreasing over time. And so after a while, you'll see like there's an evaluation step that's being done. And you see a couple of metrics here. So I'm just going to explain those so that you can really understand what's going on. Actually, that evaluation step is done on a separate, the first data set that we give as an input is randomly split between a training data set and a validation data set. So the model is only trained on the training data set and never sees the images from the validation data set. And actually, after the model has passed on each image of the data set, we'll ask the model for inferences on the validation data set, and we'll compare those inferences with the ground truth that were labeled on that validation data set. And that's how we compute some metrics. So the first interesting metrics will be the average precision. So the average precision measures on all the detections that were made by the model, what's the share of those detections that were actually correct. Okay, it can be computed with several parameters. That's why you have several lines of average precision with on the right different values. So just to explain them really quickly, here you have the IOU, which is kind of a threshold that you set in terms of overlap between the one detection of a model and a ground truth, to tell if the overlap is more than a given value, I will consider that the model was right. And if it's less than that value, I will consider that the model did not get that ground truth. So the more that value and the less the average precision. Then there is this area parameter as well. It just filter out it can filter out some of the detections that are too small or that are too big. So when it's area equal all, it doesn't filter anything. When it's small, it just takes the small detections, etc. And then there's the max depth here parameter, and this will just retain a certain number of detections among all the inferences that are made by the model, to take them into account. Of course, they're sorted by the confidence of the model on those detections, and it will just retain, for instance, 100 detections, like inferences that were made by the model, to make the computations. So now you know everything about the average precision. And we can see that after one epoch, so after the model has passed just once on each image, we can have, with some parameters, already like 52, 53% average precision, which means that 53% of the detections made by the model were actually correct. So that's already very good. And the second metric that we can see here is the average recall. So that's another metric. The recall measures out of all the ground truth inside the validation dataset, the share of those ground truth that were actually found, like detected by the model. All right. So it is subject to the same kind of parameters to make the computations. And we can see here already for the best performing set of parameters that we had 63% average recall, which is pretty good. So here it's meant to be run during 10 full epochs. So each image will be seen 10 times by the trained model. And so each time we see that the metrics are evolving, and usually until a given point, they're just going to increase. So where are we now? So here we just have, we only have just 2 epochs remaining, and the last set of evaluation has an average precision of 75%, and an average recall for the best parameters of 71%. So that's pretty good overall. Now we'll wait for the model to complete the training, and we'll try to understand that part of the process. So one important thing actually during this training process is that it created an outputs directory, which itself contains a models directory and a folder that has the name, the exact name of the training dataset. Inside that folder, you've got a list of what we call model snapshots. So those files are containing the weights of the model. So the weights of the models is all the metadata that allows us to then use that model for inference. And it also contains the different categories that the model was trained on. So it's all self-contained, and you can directly use that to make inferences. And actually, those files are going to be the input of our detect script. All right. So what we want to do right now is to make inferences on a totally blank data set. And for that, we'll be using the second data set here that's named test powerline. So as you can see, there's nothing inside. There's 0 labels. You can just go over some of the images. As you can see, there's really nothing on that. And what we'd like to do right now is just to make inferences on that data set. So for that, again, we'll use the export function of LabelFlow. So we're just going to use that export to correctly format everything in a zip file. Again, I'm not going to really do that because I want to skip the transfer time. But let's say we've done it. And again, I included it in my data folder here. That's the taste powerline COCO blah blah.zip. All right. So I think that now, okay, now the model is done training. So what we will do is, again, unzip our test data set. So we unzip our test data set. So it appears here. And now we'll just launch that detect script to see how the model performs on that raw data set. So this time, as you can see, there are 2 different inputs. Dataset path links to the raw data set that we just unzipped. It's the test one. And then there's another argument named model path. And that links to the model snapshot of our choice. So here, since the model just trained for a couple of epochs, we'll take the last epoch, but in general, you need to take care about like overfitting issues and to just look at the metrics and select the best performing ones. Okay, so I'm selecting the last one, and now I just hit enter. And it will actually create an annotation file. So annotation file is, if you recall, the JSON file that we had inside our data set. Okay, so just made it. So as you can see, it created more than 1,000 annotations. So just to give you an insight about that, when we were doing our labeling with like labeling companies, they were usually estimating 15 seconds per annotation. So here you can see it makes like 15. It would make 15,000 seconds to make the same number of annotation with a human expert, which means like more than 4 hours of work. So that's pretty productive for a model. And so right now, again, in this output directory, I can find an inference folder that itself contains an annotation file. So it has the name of the data set it was used on. That was used as an input for the detect script. So now what just remains to be done is that I need to actually transfer this file from my remote instance to my local instance. So I'm just going to do that now. So I have a small terminal here that I will use. Okay, we're done. Now I'm just opening that directory. Okay, we can see that we've got that annotation file that was created. And now again, so LabelFlow allows us to actually import this annotation file on the corresponding data set, of course. So now I'm just like importing that JSON file in my data set. So as you saw, I clicked add images, and here there's really no mentions of like how you could add like annotation files on your data set instead of adding new images. That's actually kind of a secret features as of today in LabelFlow. We really plan like really quickly to make something that is like more, that has like a better user experience overall to make you discover that feature more easily. So now we can see that it's done, like making the labels of the models. And as you can see, there are some labels that magically appeared. So we can have a look at several pictures, maybe. Here, for instance. So on that one, apparently, there was no labels. So the model sometimes just missed the labels, as we can see. But on this one, for instance, it looks perfect. So that's a tension insulator with 1, 2, 3 plates. It even codes that one, which is pretty much occluded. So that's a very good job. Here, that's a 2 plates insulator, which is rigid. So that's totally correct as well. Maybe we can find some places where it wasn't right. So here, as you can see, the model wasn't sure whether it was 3 plates or a 2 plates insulator. But I mean, anyway, you can see that the results are pretty encouraging. Here it code the transformer. those are two plates, insulators, and that's definitely a false positive. But yeah, in the end, if we recall our goal, we really wanted to have a prototype that would just make us save a lot of time, and that's the case. Like, as you can see, it gets a lot of detections correctly, and yeah, there's like it's really it would really like help us like save a lot of time, and yeah, I think I'm done demonstrating that, and I let Geoffrey hand over to show the results of our use case.
Thank you very much, Etienne, for this demonstration. So yeah, I just wanted to summarize with you the benefits that we got out of this use case. So actually, with the customer last year, the neural network was actually trained on 16 different equipments, and we could actually prove that they were saving, that they were increasing the productivity of 65%, which represents 7 man days every 1,000 analyzed pictures, images actually. And as Etienne showed you, so actually last year, so we trained the model on 1,200 images, which represented 12,000 images labels, sorry, and we inferred it on 2,500 pictures to reach this KPIs. So this is actually the analysis time per image in seconds without AI and with AI. So yeah, thank you very much for your attention. I've seen that there were like 2 questions. So the first one is actually, does your demo work for bounding box, polygons, or classification? So the answer is yes. It works with these different type of labels, and of course the JSON file and would be different depending on the labels, and also the labeling time could be also different depending on this.
And one word about the framework as well. So the LabelFlow part of things would be side of things would be would not cause any issue. From for the framework, I saw the demo for I showed the demo for only bounding boxes, and it would require some fine tuning in just one file to just import the right model from the PyTorch standard library to just adapt to those use cases, but that would be really straightforward.
Then Chen, yeah, second question. So because yeah, the last project that we've run was actually with SteerBlue. So with your experience on power grids, how many instances of insulators, transformers do you need to have good performance? And second question related is that would we need to create 2 models if some equipment look very different, for example, between 2 utility companies in 2 different geographical areas like US and Europe?
So for the first question, in general, I would say here we saw that we reach reasonable metrics with just in average 1,000 label per class. So it would mean 1,000 insulator. And in practice, like we saw that having like 10,000 labels per class would be sufficient to reach more than 90% F1 score. So that's kind of an average between the precision and the recall I talked about, which means like very, very good performance. And for the second question, we were actually not using different models for different geographic area, but again, that's really a matter of the quantity of data that you have. In general, of course, if you try to train a model with too few instances of images on two heterogeneous environments, it will fail, and you better just use 2 separate models. But in our case, we had like fairly large amount of data, so that could be done on just one model.
Thank you, Etienne. So we have one other question. Can we invite people to LabelFlow to collectively label a dataset? So stay tuned. There is a new feature which is coming. Actually, this is the hosted version of LabelFlow, and we will give the capability to label with several people in a given workspace, actually. So it's coming in the following weeks, and we'll of course let you know. Etienne, one question for you. When would you label with polygons instead of bounding boxes, actually?
Yeah, that's really a matter of the task you want to address. Here, it was just the purpose was just to do an inventory of the pieces of equipment that our customer had. So that wasn't really required to have super like fine polygons around our sets. But for instance, if you want to assess the size of a defect on an image, you usually don't want to use like just a bounding box, because it can really give like a bad estimate of the area of your defect. So I'd say for defect in general, you'll try to use more polygons, and for just inventory, you can general object detection, you can use bounding boxes.
Then there is a question, what is according to you the right ratio to spend in terms of time when you label pictures versus directly labeling the final dataset? I'm not sure to understand this question, but we can give some order of magnitude. Like usually, you know, this is what we were showing, like for electrical grid pictures. If you label manually, you will need like 280 seconds, which is roughly speaking 4 to 5 minutes, because there are many equipment to label on one picture. And if you use some AI to support you in labeling faster, you will go below 100 seconds, which means 1.5 minutes. So there is no good ratio, actually. I would say it depends, how many human resources you have internally, how well trained they are, and many different parameters, which are usually specific to your organization. So there are some threshold to build in this regard.
And in terms of AI, that also really depends on the task you want to address. Some tasks are easy for like a model to be trained on, and some others are much more intricate. And just to realize that, you really need to get a first prototype and to try it out. So that's kind of the purpose of that demonstration.
Absolutely. There is one question. I did not capture at the end of your demo. What was the file you re-upload to the platform after the training?
Yep. So that file is the annotation file that is actually a link to a COCO format dataset. So as you saw in the beginning of the demonstration, when I was explaining what is a COCO dataset, there's just a folder with images, and along with this folder with images, you've got just one JSON file that contains all the bounding boxes that are to be drawn on those images, and that makes the link with those images. And here, as an input to the script, we had the raw data set, so without any annotations. So the output of the model is this annotation file that contains the bounding boxes that we want then to import on our data set, so that we can see those bounding boxes and with the right classes.
Okay, thank you. And we have one of the last question, I guess. Is the model and the data set you showed today public? So the answer for the data is no, these data are not public yet. For the model and all this webinar, this recording, and all the different steps will be made public. Etienne wrote a README on this story, so that will be shared with all of you. All right, I think we're we are reaching the end of this first webinar of LabelFlow. So thank you to the participants. We are a pretty young team, young project. So every feedback are really welcome. And yeah, we'll be happy to continue sharing with you. Sorry, maybe one last question. We are at 43 minutes, so let's take this one. Will be the video available to Label? Not for now, but this is something that will be on LabelFlow roadmap indeed. So, but it will be probably around the end of the year, maybe a little bit further. Yep. Thank you again, everyone, and we'll share the recording with you and every information of this webinar. Have a great day. Bye bye.
Thank you. Bye bye.
Thanks, Etienne.